Hello everyone. Today we are going to discuss a very important, fascinating topic in quantum mechanics, that is wave particle duality and the de Broglie hypothesis. De Broglie hypothesis. Before entering into the mathematical part, I want you to think about one simple question. When we talk about light, how do we normally understand it? For a long time, scientists had two different ideas about the nature of light. In some experiments, light behaves like a wave. In other experiments, light behaves like a collection of particles called photons. This was one of the major developments that led to the birth of quantum physics. Now, an interesting question arises. If radiation, which we traditionally consider as a wave, can also behave as particle, then can matter particles also behave as waves? For example, can an electron behaves like a wave? Can a moving material particle have a wavelength associated with it? This is exactly the question that Louis de Broglie considered in 1924. His revolutionary proposal was that matter also possesses wave particle duality. That means a moving material particle is associated with a wave, which we will call matter wave or de Broglie wave or pilot wave. A material particle accelerated with light velocity and producing a wave. That wave is known as matter wave or de Broglie wave or pilot wave. That particular wavelength is called de Broglie wavelength. Today we will understand what this statement means, how wavelength is obtained, what physical quantities determined the wavelength, and why this concept is important for modern technology. We will also see why quantum effects are very important when we study very small particles such as electrons, protons. So, by the end of this lecture, I would like you to remember one central relationship. The wavelength associated with a moving particle is inversely proportional to its momentum. We can discuss. So the mathematical expression for this relationship is the de Broglie wavelength. So let us begin our discussion by asking some basic curiosity questions. Curiosity questions. So trying to see here. So if light behaves as a particles, photons like, so could electrons also behave like waves? You see here, why do not have observed wave behavior in everyday objects like cricket balls or cars? So what I'm saying, try to understand here. Now look at the two questions on the slide. The first question is already I discussed. If light behaves as a particle or photon, could electrons also behave like waves? And the second question, why do not we observe wave behavior in everyday objects like cricket ball or car? There are excellent questions because they take us directly into the heart of quantum mechanics. Let us first think about electrons. An electron is material particle. An electron is a material particle. From classical physics, we normally think of a particle as something located at a particular position and moving along a definite path. A wave is very different. For example, water waves spread through water, sound waves propagate through a medium, electromagnetic waves can propagate through space. Through space. So the classical picture tells us that particles and waves are completely different types of physical entities. But quantum mechanics tells us that this distinction is not always valid. At the microscopic level, particles such as electrons can demonstrate wave like properties. If electrons can have wave characteristics, why do not have see the cricket ball behave like a wave? According to de Broglie idea, even a large object can be associated with a wavelength. But the important point is the magnitude of the wavelength. The de Broglie wavelength depends on momentum. You can see here momentum. Momentum is the product of mass and velocity, m into v. So, for a large object such as a cricket ball, the mass is comparatively large. Therefore, its momentum is large and the associated wavelength becomes extremely small because of lambda is inversely proportional to momentum. Lambda is inversely proportional to that mass of the object. When the wavelength becomes extremely small compared with the dimensions of the experimental systems, wave effects become particularly unobservable. For microscopic particles, such as electrons, however, the mass is extremely small. Therefore, their de Broglie wavelength can become significant and suitable momentum. This is why quantum mechanical wave effects are especially important at microscopic scales. So remember this important idea matter waves are not restricted to electrons alone. The wavelength is associated with momentum, and the visibility of wave behavior depends strongly on the scale of the wavelength. So this idea leads under directly to de Broglie hypothesis. De Broglie hypothesis. You try to see here de Broglie. Why de Broglie hypothesis for computer science students? So try to understand here. Now let us another important question. Why should computer science students study the de Broglie wavelength? At first, you may think that this is purely a physics topic, but look carefully at the applications shown on the slide. The first major area is nanotechnology and electronics. As electronic device become smaller and smaller, quantum effects become increasingly important. So modern electronic system operate at dimensions where classical description alone are not sufficient. So the specifically highlights it is you can see here electron transport in nano devices, quantum dots, carbon nanotubes, two-dimensional materials. These are all important areas in modern technology. Modern technology. Let us consider electron transport. So you can see here electron transport. In conventional electronic circuits, we often think about electrons simply as a charge carrier moving through conductors and semiconductor devices. But when the dimensions of a device become very small, the wave nature of electron becomes important. So the second example, quantum dots. Quantum dots. So quantum dots are nanoscale systems in which quantum confinement strongly affect electronic behavior. So another one is carbon nanotubes. Carbon nanotubes. These structural or these structures have nanoscale dimensions and their electronic properties are closely connected with quantum physics. We also have two-dimensional materials. When matter is confined to very small dimensions, quantum mechanical effects become increasingly important. This slide, this is also connects quantum mechanics with computational science. Computational science. So we have molecular simulations, material modeling, drug discovery, and computational chemistry. These fields use computational models that describe microscopic systems. The important message for computer science students is that modern computation is not separated from physics. Computer simulations are used to model molecules, materials, electronics, structure, and other microscopic systems. So, quantum mechanics provide the physical function foundation, while computer science provides the computational tools needed to model these systems. Therefore, when you study the de Broglie hypothesis, do not think of it as simply another formula to memorize. Think of it as one of the fundamental idea behind our understanding of matter at the microscopic scale. So coming to quantum mechanics, de Broglie hypothesis. De Broglie hypothesis. So in 1924, de Broglie introduced his hypothesis. The first statement is that the universe consists of matter and radiation. You try to see here, the entire universe consists of matter and radiation. So you see here in 1924, de Broglie made few hypotheses for dual nature of matter waves. They are number one, the first statement is that the entire universe consists of matter and radiation. The second one you can see here, nature loves symmetry or close parallelism between optics and mechanism, or radiation and matter. So this is a very powerful idea. Scientists had already discovered that radiation could have in both wave and particle forms. So de Broglie asked, why should this duality belonging only to radiation? Why shouldn't matter also show a similar dual nature? This led to the third statement. So you see, third statement, matter waves also exhibit dual nature like radiation. This means that a material particle can have both particle characteristics and wave characteristics. The fourth statement you can see here, the wave associated with material particles are called matter waves or de Broglie matter waves. Its wavelength is called de Broglie wavelength. De Broglie wavelength. Now, remember that a matter wave is not simply an ordinary mechanical wave like a matter wave. The concept belonging to quantum mechanics, the important physical idea is that a moving particle has wave characteristics as well as with it. This was a major conceptual change in physics, especially in quantum mechanics. So, classical physics separated particles and waves. Quantum physics brought them together. So, we can summarize the central idea of this slide in one sentence. Just as radiation has wave particle duality, matter also possesses wave particle duality. This is the foundation for everything we discuss in the today's lecture. So now coming to matter waves. Now let us define matter wave more precisely. According to de Broglie hypothesis, a moving particle is associated with a wave. This wave is called de Broglie wave or simply the matter wave, or also it is called pilot wave. That particular wavelength is called de Broglie wavelength. So what I am telling here, definition, you try to understand here. In 1924, de Broglie extended his hypothesis radiation to material particles. The material particles are accelerated with light velocity. It produces some wave is called matter wave. Matter wave. So you see here, definition also you can see here. According to de Broglie hypothesis, a moving particle is associated with a wave which is known as de Broglie wave. So that particular wavelength is known as de Broglie wavelength. De Broglie wavelength lambda is equal to h by mv or lambda is equal to h by p. P is the momentum. The product of mass into velocity gives the momentum. So you can see here lambda is equal to h by mv or h by p. So expression for de Broglie wavelength, try to understand here. So consider the Planck's theory of radiation. The energy of photon is given by E is equal to h nu. For example, this is nu is equal to c by lambda. Therefore, E is equal to hc by lambda. Let this is equation number one. Equation number one. So according to Einstein mass energy relation, the energy E is equal to mc square. Let this is equation number two. But left side both are same. Energy in equation one, energy in equation two. So we can write equation two is equal to equation one, or equation one is equal to equation two. So I am taking here equation 2 mc square, that is equal to equation 1 hc by lambda. So in this square c, this c gets cancelled. Lambda is equal to h by mc. You can see here in equation 3. If we consider the case of material particles of mass m moving velocity v, therefore let at the place of c we can take velocity, moving velocity v, material particles mass m, materials particles moving velocity v. Therefore, at the place of c we can take lambda is equal to h by m into v. So this is v. Or lambda is equal to h by p, where p is equal to mass into velocity. Okay, coming to next one. So in 1924, Louis de Broglie extended the wave particle dualism of light to the material particles. Not only the light, but every materialistic particle, such as electron, proton, or even the behavior object, exhibit wave particle dual nature. So, try to understand here. In 1924, Louis de Broglie extended the wave particle dualism of light to material particles. This was a revolutionary proposal. Previously, wave particle duality was primarily associated with radiation, but de Broglie proposed that the same type of duality should also apply to matter. So try to understand this. It gives the example also you can see here. The examples such as the electron and proton, and also points out of the even behavior objects can in principles have associated matter waves. The important word here is moving. According to the hypothesis, a moving particle has waves associated with it. These waves are called matter waves. These waves are called matter waves. Now, we need to be carefully about how we interpret this statement. It does not mean that an electron is literally a small particle. Instead, it means that the behavior of a microscopic particle must be described using quantum mechanical wave concept. This is one reason quantum mechanics is fundamentally different from classical mechanics. In classical mechanics, we usually imagine a particle following a trajectory. In quantum mechanics, the wave description becomes essential. So coming to next one, de Broglie wavelength in terms of kinetic energy. De Broglie wavelength in terms of kinetic energy. So, so it introduces the de Broglie wavelength in terms of kinetic energy, capital E. So this form is particularly useful when a problem gives the kinetic energy of the particle instead of its velocity or momentum. We already known. So the kinetic energy represented by E is equal to half mv square. So kinetic energy E is equal to, I am taking as it is half mv square. So it is multiplying with m and also dividing with m. So m into m here you can see m into m square. Already v square is here, all divided by this 2 into m, this is 2m. So E is equal to this mv whole square, I am taking m square v square, I am taking mv whole square by 2m. But momentum p is equal to, we know, mv. So at the place of mv, I am taking p, so whole square by 2m. Kinetic energy is equal to p square by 2m. From this relation, p square is equal to 2m e. That is equation number 2. But de Broglie wavelength lambda is equal to h by p. So this is, we can write p is equal to root of 2m e. So substitute this p value here, we get lambda is equal to h by root of what is p? 2m e. So this equation is known as de Broglie wavelength in terms of kinetic energy E. De Broglie wavelength in terms of kinetic energy E. So again, you try to understand here, the kinetic energy E is given by E is equal to half mv square. So half mv square, I am taking as it is, multiplying with m, it is dividing with m. So here, m into m square, already v square is here. So I am taking here v square as it is by 2m. So we can write this is mv whole square divided by 2m. So this is mv square by 2m. What I am taking here is equal to mv whole square divided by 2m. So this is equal to mv, that is a p square by 2m. So here E is equal to p square by 2m. We know very well p square is equal to 2m e. P is equal to whole root of 2m Now substituting this p value in lambda is equal to h by p, h as it is at the place of p, that is 2me. So that equation is known as de Broglie wavelength in terms of kinetic energy E. So coming to next one, de Broglie wavelength, de Broglie wavelength associated with an electron. The electron is one of the most important particles in quantum mechanics because it is very light and its wave nature can become significant. When we associated a de Broglie wavelength with an electron, we are saying that the electron has both particle characteristics and wave characteristics. The particle description tells us that the electron has mass, momentum, and also energy. Because you try to understand here, you try to understand electron mass, it has the mass 9.1 into 10 to the power minus 31 kg. So electron has mass. Electron is moving with velocity. It has m into v. It has momentum. So, for example, kinetic energy or any energy of m into v square. So, what I am telling here simply the particle description tells us that the electron has mass, momentum, and energy. The wave description tells us that it has an associated wavelength. This idea is extremely important in electronic and nanotechnology. Why? Because modern electronic devices increasingly operate at very small dimensions. When the dimensions of a device become comparable to characteristic quantum scale, classical descriptions are no longer sufficient. The wave nature of an electron becomes important. This is connected with several topics mentioned earlier in the presentation, such as electron transport in nano devices and quantum dots. Now, think about the equation. So, if velocity v is given to the electron by accelerating it through a potential difference v volts, then the work done on the electron is EV. So, for example, you know very well the potential difference V is equal to work done per positive unit charge. So, here I am taking voltage as it is, work done W as it is, the charge I am taking electron charge. So, work done is equal to E into V. This work done treated as potential energy. Potential energy. So, potential energy is equal to EV. What I am saying here? So the velocity v is given to an electron by accelerating it through a potential difference of v. Then the work done on the electron that is treated as potential energy E into V. Let equation number one. So kinetic energy we know very well. Kinetic energy is equal to half mv square. Already we discussed multiplying with m and dividing with m. So this is equal to m square v square by 2m. That is mv whole square by 2m. mv whole square, that is p square by 2m. So here at the kinetic energy is divided into potential energy. The potential energy is converted into kinetic energy. The kinetic energy is converted into potential, and potential energy is converted into kinetic energy. At a particular point, the kinetic energy is equal to potential energy. So kinetic energy, I am taking here P square by 2m or half mv square, you can see here, is equal to potential energy E into V. From this relation, so P square is equal to 2m EV. P is equal to root of 2m EV. 2m EV. So here, just to take this V and substitute here, we can get, or lambda is equal to h by p, just to substitute h by root of this one, p value substitute here, 2m ev, 2m ev. So this is the de Broglie wavelength associated with an electron e, associated with an electron e. Like this also we can observe, or another one. So this is kinetic energy is equal to, this is potential energy. So kinetic energy is half mv square. Potential energy is equal to E into V. From this relation, potential difference is equal to, we can write 2EV. So this is V, velocity V square. From this relation, velocity V square is equal to 2me by m. So V is equal to root of 2Ey by m. So substitute this velocity here. Then otherwise we can also write this is mv is equal to, we can write root of 2mev. Substitute here lambda is equal to h by root of 2mev. This is the de Broglie wavelength associated with an electron. So one exercise problem you try to understand here. For an electron mass 9.1 into 10 to the power minus 31 kg, Planck's constant h is equal to 6.625 into 10 to the power minus 34 joule second. Charge of electron 1.6 into 10 to the power minus 19 coulombs. Substituting this constant we get. So here lambda is equal to root of, lambda is equal to, try to understand here, lambda is equal to h by root of 2m ev. So already they mentioned the mass of electron 9.1 into 10 to the power minus 31. Planck's constant 6.625 into 10 to the power minus 34. Electron charge 1.6 into 10 to the power minus 19. Substituting all the values in this equation at the place of h. So Planck's constant 6.625 into 10 to the power minus 34 joule second, whole root of 2 as it is. So mass, this is the mass of electron, this is charge of electron, this is potential difference. So after calculation, we can get lambda is equal to 1.227 into 10 to the power minus 9 meters. Or wavelength is equal to, we can take 1.227 by root V nanometers. 1 nanometer is equal to 10 to the power minus 9, or lambda is equal to 12.27 root V angstroms. Angstroms. So coming to today's summary. Introduced the idea of that all matter exhibits wave-like behavior with wavelength inversely proportional to momentum as proposed by Louis de Broglie. This wave particle duality bridges classical and quantum physics, laying the foundation for quantum mechanics. We began with the idea of wave particle duality in this lecture. We discussed how radiation can show both wave and particle characteristics. Then we asked whether matter could also possess wave characteristics. Louis de Broglie proposed the answer in 1924. He suggested that moving material particle is associated with a wave. These waves are called matter waves or de Broglie waves. We discussed clearly in this video. The wavelength associated with a particle is called de Broglie wavelength. The most important equation from today's lecture, we discussed de Broglie wavelength lambda is equal to h by p. That is equal to lambda is equal to h by root of 2me. This is the de Broglie wavelength in terms of kinetic energy. That is equal to h by root of 2m ev. So de Broglie wavelength associated with an electron, we clearly discussed in this video. We also discussed why wave behavior is important for microscopic particles such as electrons. For microscopic objects, the associated wavelength is generally extremely small, so the effects are not easily observed. Finally, we connected the de Broglie hypothesis with modern applications such as nanotechnology, electronics, quantum dots. So, if you remember only three things from this lecture, remember first, matter has wave particle duality. Second, a moving particle is associated with a matter wave. Third, the de Broglie wavelength is given by lambda is equal to h by p, lambda is equal to h by root of 2me, lambda is equal to h by root of 2mev. These 3 points from the foundation of today's topic we clearly discussed. Thank you, everyone. Before we close, let me give you a few questions to think about. First, what is the de Broglie hypothesis? Second, what is meant by a matter wave? Third, write the expression for the de Broglie wavelength. Why is the wave nature of an electron more important that of the cricket ball? And finally, what happens to the de Broglie wavelength when the momentum of a particle increases? If you can answer these five questions confidently, you have understood the fundamental concepts of today's lecture. Let us once again remember the central equations. Lambda is equal to h by p. So, in our next class, we will discuss another topic. Thank you so much. Thank you. Thank you, everyone.